Hello, it's Keith here, and this is lesson 5 of the Photon series, and it's going to be the last one we discuss this rotten multi-platform code because I'm getting quite bored of it, and I'm sure you are too. We're going to be looking at the player code that handles the multi-platform player sections. That is the parts that are common to every system. The joystick reading is platform specific, but this is multi-platform code. And we're going to look at the CPU AI, which is how the CPU decides when it needs to make a quick turn to get out of the way of stuff. So that's what we're going to be looking at today. Okay, well, let's go over to the source code and let's have a look. Now, we will probably just need to actually have the game running because we might need to discuss some parts of it at some point. So we'll just load that up and let's go over the code we're going to be looking at today. So the handle player routine is used to draw the player to the screen and handle things like boost power. Boost power is when you press the fire button and it increases your speed. Well, let's just see that for starters. So if we just load this up here and if I press fire here, now if I hold down fire here, you'll see I move faster than normal and you can see the boost power goes down. Now the reason this was implemented is so we can chase the CPU and catch up with them if they're further ahead than us, because otherwise it's not going to make much fun to the game. Now you can see the CPU is able to, with some intelligence and only limited, detect an object in front of it and move out of the way. Now you can see it's waiting quite a distance, it's looking quite far ahead before it makes its move, and basically that relates to the CPU AI. Effectively the AI is set to 7. That means it's looking 7 pixels ahead and responding to an object 7 pixels ahead, but we can catch it out if we get in the way before those 7 pixels. But if I get in the way of the CPU and it doesn't have time to respond, it will crash straight into me, as you saw just there. So the CPU's AI is relatively dumb, but it's enough to make a little fun game. So first of all, what we're doing here is we're checking the boost power and seeing if the boost is on. And if the boost is on, then we're going to reduce the boost power if we've got any, and we're going to process this tick. Now if the boost is not on, we're going to check the tick and check if we want to move or not. If the boost isn't on, then we're only going to actually move every other tick, so the game doesn't do anything for one tick, and that's how we do the half speed. So if the boost power is on, then what we want to do is we want to check all but the last bit. Now the shown boost power might be 90, but the actual stored value in memory is 180. So we're ignoring one bit and we're seeing if we need to change the boost power. If we don't need to change the boost power, we do nothing. But if we do need to change the boost power, then what we do is we draw the old boost power in color 0, clearing it off the screen, and then draw the new boost power over the top. And we're using color 1 to show the new boost power here. So that will update the number in the corner. The vector routines aren't very fast, unfortunately, so we have to try and keep things as limited as possible to keep the game running nice and fast. Although I think they've got a little bit faster recently. I think I did some optimization on them and they're slightly better now. But basically that is updating the boost power on screen if we need to. Here we're decreasing the boost power, and then this routine is checking if boost is set or if the tick is odd, and if neither of those are the case, then we're skipping over to here and we're just going to return. This is the routine that's going to move and update the player if we need to. So to move the player, what we do is we add the acceleration of the player, which is a word, to the player position for X and Y. That will move the player. These are the direction that's set by the other routines. So this will move the player. We then load the position of the player and we test the new position of the player, and we see using the point function, and that's a platform specific function to read a pixel from the screen and see what color it is. If it's 0, then it's the background. If it's non-zero, we've collided with something, and that means we've got a problem. So if we've collided with something, we decrease the lives of the player. If the player's got lives left, we go back to and restart the level. If the player has no lives left, then they've died, so we show the game over message. If they're not dead, if they've not hit an object, so point was returned as 0, then what we're going to do is we're going to set the pixel that represents the new player's position to the color of the player, which is color 2. So that's drawing the player to the screen. Now, we're just going to very quickly look at the platform specific code, which we are going to look at next time. But whenever we need to update the position because the player's turned, because we turn in 90-degree rotations, we are altering the direction in HL, and then we're running set player direction. And that set player direction is this common code just here. So what we're doing is we're getting the player direction, we're limiting it to 4 directions, we just keep rotating around if we keep rotating, and then we're loading in the template of the directions. There are 4 bytes per direction in that template, and then we're copying 4 bytes from the template to the player's current position, and the player's current position will be in IX here, and we're loading in player X acceleration here, but that's actually the start of the player definition. If I go to ramdefs here, you can see that those two are consecutive. So we're effectively filling these 4 bytes here from these 4 directions here. And so these are an X and a Y acceleration. So -1 is going up the screen, 1 is going to the right, -1 is going to the left, and 1's going down the screen. So these are the directions here. And so we're just copying 4 bytes of one of these according to the direction that is currently selected. That's how it works. So that is turning the player around there. Now, here's the CPU code, and the CPU code is quite different and a bit more complicated because it's having to do some intelligence of sorts. So what we're doing first is we're checking the tick, and we're only updating the CPU every other tick. Now, the player can update every tick with boost. The CPU doesn't use boost. The boost was really an thing to make the player have the chance to catch up with the CPU, because otherwise, if the CPU got ahead of you, it'd be very hard to do so. So it was really to make the game more fun than it actually necessarily benefits you, because often you end up dying because you've crashed into things. Anyway, so we're checking if the CPU is going to be updated this tick, and then what we're doing is we're loading the X and Y position of the current CPU and the acceleration into BC, and we're first adding the acceleration of X and Y to the player position, but then we're running this apply AI function, and you can see this down here. Now what this effectively does is it is effectively multiplying BC by the CPU AI and adding it to HL, and this is how we do the look ahead, because if our CPU is here moving in this direction and we add 1 lots and lots of times, we'll end up looking at a pixel further ahead here, and then we're going to do our test and see if that pixel will cause a collision. That's how our CPU looks ahead and how our AI affects where the CPU looks. And that's what we're doing here. So we're backing up the X and Y position of the CPU for later, and that's for the turn checking code. But then what we're doing here is we're checking the point that the CPU is currently looking at thanks to its AI. If the point is 0, then the CPU is perfectly happy. It's not going to do anything. Otherwise, the CPU is going to have to make a turn. Now, by default, the CPU turns in the same direction every time, but there's a random chance it will change its direction and start turning in the other way, just so the user can't entirely guess what the CPU is going to do, basically. So we've got a random number here, and if that causes a turn, we're going to flip the CPU's turning direction around here. Otherwise, we're just going to carry on. Now, if the CPU is looking in this direction, there's going to be 3 potential alternate directions here. So we're setting B to 3 for 3 tests, but we don't want to test directly in the direction the CPU came, because obviously that's going to be no good. So we're checking that here. We're checking our turns here, and we're skipping over direction 2 because 2 would be facing in the entirely opposite direction to the one we started in, so that's not going to help. So that's what we're doing there. And then what we're doing here is we're loading in a direction here. We're loading the attributes of the direction. That's the same ones as the CPU, as the user player used. Where are those? That's these again. So we're loading in one of these directions here, and we're seeing how that is going to affect the CPU's lot in life, so to speak. So this CPU test here will do that. We're loading in the CPU position, adding that change, and we're then testing the point that that will result in if the CPU tries to move in that direction. And if that will stop the CPU from colliding into anything, then we will consider that valid, and we will return a non-carry. If that's going to cause a collision, we will return a carry. And that's what's happening here. And as soon as we get one that looks like it's okay, we're going to move down to here. Otherwise, we're going to move back up, and we're going to read in another direction, and we're going to try again. That's what we're doing here. So we're trying the directions to see what one will help the CPU out of its hole, out of its problem. So that's what we're doing there. When we get to here, whatever's happened, we've decided what direction the CPU is going to go in, and so we're going to apply that. So we're loading in the acceleration, applying it to the CPU, and then what we're doing here is we're testing the point that the CPU is now ended up on, and then we're seeing if that has collided. If it has, then the CPU has died, so we're giving the player a leg up to the next level and restarting that next level. Otherwise, the CPU is still okay, and we're showing the pixel to the screen. Now, of course, we're checking the point here. This is the point that the CPU has actually hit. This is the point up here that the CPU is looking at for making its decisions, of course, which will be very different. If the CPU is here and it's very stupid, it will be looking here for its decision making, but the point it's actually going to collide with will be all the way over here. And the closer to the actual point the look ahead is, the tighter the CPU will move compared to the walls, and the harder it will be to trap the CPU, hopefully. So that was the simple AI that I created here. I'm not claiming it's a good way of doing things. It was just good enough, really. And that's all there is to it. Now, of course, you could make the AI a lot smarter. You could make the look ahead work the other way around so that the CPU actually looks at all of the pixels in a line towards the look ahead level. And if any of them are a problem, it could decide to move or something like that. And you could, before it decides on a potential turn, it could look ahead in that direction and see how cluttered it looks like it's going to be if it turns to the left compared to if it turns to the right, things like that. But as I say, this was just a very simple game. It was outside of the scope of what I was trying to do in these tutorials and in this game to do that. So that's all we're covering today. This is the end of the multi-platform Photon tutorials. We're going to go to platform specific stuff, and we're going to start looking at joystick reading, which is basically the same as YQuest, so we won't cover that very much. But we're also going to look at the more important point testing, reading pixels off the screen, and pixel plotting, putting them on the screen. The line routines are all multi-platform. They just use that preset routine, so that's not going to be something we're looking at. But as I say, it's all to do with if you want to draw vector graphics, really, and hopefully it'll be interesting to you if you need to know more about that. Anyway, I hope you've enjoyed this. I hope it's been interesting to you. As I always say, you can get all of the source code for this off my website. You can do whatever you want with the code, and you can make your own games out of it if you manage to do that. You don't need to give me credit for something. I'm sure you would deserve all the attention you manage to get for it. But anyway, whatever you decide to do, I hope you have a lot of fun with your Z80 programming, and I wish you all the best with it. Thanks for watching today, and goodbye.